Hello, I'm going to review everything for Chapter 6 on solving systems of equations. So the first problems I'm going to go through are just a couple precision things. I'll do 2 problems on solving using substitution, and then 2 of them using that linear combinations, which was called elimination. So in this first example, what we're really looking for is one equation where the variable is isolated, so all by itself on one side of the equal sign. In this case, we have a y equals equation. So what I'm going to do is box up the expression that comes after that, and we're going to substitute it into the top equation for just the y variable. So we're still going to leave the 3 there. We're just going to substitute it and basically replace the y. And now I'm going to rewrite this entire top equation. So 4x plus 3 times our quantity here from the box, the 2x minus 7, and that equals 4. So what we're going to do now is distribute to solve this equation. 4x plus 6x, and then I have 3 times negative 7 is negative 21, and that equals 4. I have like terms here, so I'm going to combine these like terms. 4x plus 6x is 10x. And now what I want to do is bring my 21 over to the other side. So much algebra. And so I end up with 10x equals 25. So then your last step is to divide both sides by 10. Bam! X equals 25 divided by 10, which is 2.5, and you can definitely get a decimal. Okay, it just means that on the x-axis, your x part of the coordinate, because again, we're really solving for the coordinate where these two lines intersect, your x-coordinate is 2.5. So what we really need now is the y part of the coordinate. So I'm going to take my x value, and it really doesn't matter what equation you substitute it back into. I highly recommend putting it into the bottom equation and substituting it in for x down here, because y is all by itself. So y equals 2 times our x value of 2.5 minus 7. 2 times 2.5 is 5, and 5 minus 7 is negative 2. So our x value was 2.5, and now our y value for that coordinate is negative 2. And again, with the substitution equations, what you're really looking for is that one variable to be isolated before you can substitute. So in this next one, it's kind of a different setup since y is isolated on both of these. So I'm still going to do the same thing. I realize what y is equal to. I'm going to take this expression and I'm going to substitute it into my other equation for y, just like I did in the first example. So I'm going to replace the y up here and write 4x minus 9 equals, so that covers my left-hand side. Now I'll bring down the negative 2x plus 3, and we'll solve this. So I'm going to add 2x to both sides first, so I can get my variables on one side of the equation. So I get 6x minus 9 equals 3. And then what I'm going to do to both sides is add my 9 to bring it over. Get 6x equals 12. And then what I want to do is divide both sides by 6. So I end up with an x value of 12 divided by 6, which is 2. So again, that is just the x part of the coordinate. We need to figure out the y part of the coordinate. So I'm going to take this value, substitute it back into either one of these equations. It really doesn't matter. Again, I'm just going to encourage you just to substitute it into our box that we had circled originally. So y equals 4 times our x value minus 9. So that's 8 minus 9. So I get a y value of negative 1. And again, what we're really doing is trying to find where these two lines intersect each other. Just to prove to you guys, knowing something that you have seen before, I'm going to take the calculator and show you guys on a graph what this would look like. So let me shut this off. Okay. So you don't have to do this part, but what I'm going to do is go to y equals, and I'm going to show you, I'm going to put both my equations in here. Y equals negative 2x plus 3. In my other equation, y equals 4x minus 9. And it was nice that both of these equations were already in slope-intercept form. And now I'm going to hit graph, and what I'm really looking for is an intersection at the point 2, negative 1. So it looks like it's about right here. I'm going to hit second trace, and again, you do not have to do this. I'm just checking my answer to prove again that both of these lines do intersect at that coordinate, and there's our answer. The x value of 2 and the y value of negative 1. So anytime you want to check your answer, you can either substitute your x coordinate and y coordinate into both equations, or you can solve using the graph. So for the next ones, we are going to solve these ones using elimination, which we call linear combination, which is where we're trying to eliminate a variable by adding the two equations together. So you're combining two linear equations. That's why it's called linear combination. So let's say I want to eliminate my x values. If I were to do that, I would need to find some kind of multiple that 3 and 4 go into, and that means I would really have to multiply both equations. It looks a lot easier if I want to eliminate my y's, because in order to cancel a positive 2y, I would need the top equation to say negative 2y, because you want opposites so that one of these will be positive, the other one will be negative, which means in order to make this top equation turn into negative 2y, I need to multiply everything by negative 2. Everything going across the top. So negative 2 times 3x is negative 6x. Negative 2 times y is negative 2y. And negative 2 times 17 is negative 34. So I have my top equation rewritten. I'm going to just basically bring down the bottom equation. And again, the goal of doing this is that we are going to be able to add our systems going straight down, or I'm sorry, add our equations together going straight down, and our y's are going to eliminate. So I have negative 6x plus 4x, that's negative 2x. The negative 2y and the positive 2y are going to cancel each other out or eliminate. And then negative 34 plus 20 is negative 14. So at the very end, I'm going to divide both sides by negative 2 and end up with x equals negative 14 divided by negative 2, which is positive 7. So now that I have this value, it does not matter, just like with the substitution problems, it does not matter what equation you substitute it back in for. So I'm going to pick the top one because y is all by itself with a coefficient of 1. The number in front of y is technically 1. So what I'm going to do is substitute my value of 7 in for this x. And now my only variable here is y, so 3 times 7 is 21, plus y equals 17. And if I subtract 21 on both sides, I'm going to end up with y equals, and 17 minus 21 is negative 4. So at the very end of this problem, you want to express your answer as a coordinate to really show me where these two lines crisscross, and it is at the point 7, negative 4. Okay, and also another vocab word just to touch up on. Since we do have a solution, we call this a consistent system. If we had infinitely many solutions, we still technically have a solution. You would just end up with one line on top of another, and that would mean it would still be a consistent system. The only time when you have an inconsistent system is when you would have two parallel lines that will never touch and never intersect each other. So the next one, another elimination problem. This one's going to be a little bit more work, and the reason is because there's nothing I'm going to multiply 2 by, like a whole number that's going to get me to 5, and there's nothing I can multiply this 2 by to get to 3. So what I am going to do is try to find a common multiple, and I'm going to use my y values. The reason I'm using these is they are already opposite signs. My x's are both positives, so I'm going to take the y's, and if I want to find something to eliminate my y's by, I need a common multiple for these. So my common multiple is going to be 6, because 2 times 3 is 6. So what number does 2 have to be multiplied by to get to 6? That would be 3. And what number does the 3 have to be multiplied to get to 6? That would be 2. So I'm going to multiply straight across the top, and the 2 is going to be straight across the bottom. And again, the reason why I don't have to multiply one of them by a negative value is because they are already opposite signs. These coefficients are opposites. So I end up with 15x minus 6y equals, and that's 144. And then the bottom equation, 2x times 2x is 4x, 2 times 3y is positive 6y, and 2 times negative 23 is negative 66. Or, I'm sorry, negative 46. What am I thinking? Okay. Blah, 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 blah. Now I'm going to go straight across. Again, what we're going to do is add. We are adding our two equations together, and what our goal was is for our y's to eliminate. So what I want to do is add my x's going straight down. 15x plus 4x is 19x. And again, my y's are going to eliminate. And then I'm going to set 19x equal to negative 190. That's what negative 144 plus negative 46 is. And if you divide your answer, you're going to end up with x equals negative 10. Okay, so again, now that I have my x value, I can substitute it back into either equation to get a y value. So I'm just going to pick the top equation, no reason. So 5 times our x value minus 2y equals negative 48. This comes out to negative 50. Minus 2y equals negative 48. I'm going to add 50 to both sides. So I end up with negative 2y equals positive 2. And then at the very end, I'm divide both sides by negative 2. And 2 divided by negative 2 is negative 1. So my final answer expressed as a coordinate is the point negative 10, negative 1. Okay, so now we get into the fun stuff, story problems. The first one I'm going to do, well actually they're both different story problems as far as setup and the way we're going to solve. So we're going to define variables, set up our equations, and then solve the equations. We're going to graph them, so we're going to do all the good stuff. So Mike's buying shirts and pants. He has a total of 12 items. Shirts cost $10, pants are $25. He spent a total of $180 on all of his 12 items. How many of each item did he buy? So how many of each item did he buy? So I always bring us back to this bottom sentence because this is going to help us define our variables. So we want to know how many of each item between shirts and pants. So our variables are not S equals shirts and P equals pants, because that means you could be talking about price, and we're not talking about the price here. We're talking about at the very end of it, how many of each. So S is going to represent the number of shirts that he bought, and P is going to represent not the price, but again, the number of pants that he bought, the pairs of pants. So I want to write two equations, so one system. He has a total of 12 items, so if I take all the shirts that he bought and all the pants and I add them up, it has to be 12. So S plus P equals 12. So that's when he gets to the counter and he just hands them his number of items. Whatever the combination is, it has to add up to 12. Now when you're charging money for this, it's $10 per shirt, so $10 times the number of shirts that he has, plus $25 times the number of pairs of pants that he have, that came out to $180. So I have two equations written in standard form. I know they're in standard form because my variables are on the same side of the equal sign. And what I want to do is solve this equation, this system, using elimination. Since it's written in standard form, elimination or a combination of linear systems will be, linear equations will be the easier method. What I'm going to do is try to eliminate my S variable. So it really doesn't matter, either one is going to have the same level of difficulty and the same process. If I want to eliminate my S's, I need something to cancel out with positive 10S. So I need this top equation to say negative 10S, which means I need to multiply everything by negative 10. So I'm going to do it right next to it, negative 10S minus 10P equals, and that would come out to negative 120. And below that, I'm going to have my other equation, not changing a single darn thing. 10s plus 25p equals 180. Now that I have one of my variables to be eliminated, I'm going to add my equations going straight down. So the s eliminates. Negative 10p plus 25p is 15p. And negative 120 plus 180 is 60. So at the very end of this thing, we're going to divide both sides by 15, which means he bought 4 pairs of pants. And what I'm going to do in order to figure out how many shirts he bought, I just know that this top equation, I'm going to substitute it back into that because his combination of shirts and pants has to come out to 12 total items. So however many shirts he bought plus the 4 pants equals 12. So I'm substituting my p-value into the top equation. And if I just subtract 4 on both sides, it means that he bought 8 pairs of pants. Or I'm sorry, 8 shirts. So at the very end of the problem, it says how many of each item did he buy? Answer in a sentence. Say, Mike bought 8 shirts and 4 pairs of pants. Okay, so you want to put that sentence at the very end. That's how you get that 4 for an answer, because it is a problem-solving problem, and we want to answer our question in context of the situation. So I'm going to go to the graph now. I'm going to get rid of some of this work just to clean this up. I'll still keep my solution hanging around that the number of shirts was 8 and the number of pants was 4, so I'm going to bring this up here. And the reason I'm going to do that is just to hang around with that, because we are going to see an intersection for these two values. And I want to show that, again, our intersection is going to be at the point 8, 4 if I decide to plot my shirts on the x-axis. So I'm going to put number of shirts down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm just counting spaces here by ones, and I'll do the same thing up here too. 3, 4, 5, 6, 7, 8. Okay. So what I'm going to do is take both of my equations that I had before, which one of them was s plus p equals 12, and the other one was 10s plus 25p equals 180. And I'm going to graph this using intercepts. So I'm going to look at this top equation, and again, we're going to have two lines here. So I'm going to use 4 points to make up two lines. In my top equation, if he buys 0 pairs of pants, in other words, if I substitute 0 into this equation, in for p, it means s is 12. If he buys 0 pairs of pants, that's 12 shirts. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I put 12 over here. And I'm going to do the same thing for the pants equation then. If he's selling 0 shirts, or buying 0 shirts, then that means he's buying 12 pairs of pants. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And again, once you have 2 points, I'm just going to connect the dots, change my color. Spectacular. Sweet. Now I'm going to go to my other equation. I'm going to do the same exact thing. Let's pretend that he buys 0 pairs of pants. So this term goes away, and I would be left with 10s equals 180, which means that if he had 0 pants, that means he would have 18 shirts if you were paying that kind of money. So I'm going to have to keep this going up. If this was 12, 13, 14, 15, 16, 17, 18, it would be all the way the heck up here. Oops. Wrong axis. My bad. This should be number of shirts. So I should be doing this across the x-axis, which means I'm horribly going to have to move this graph over. Oh boy, oh boy, oh boy. Cool. Maybe this isn't as bad as I thought it would be. Good enough. Okay, I'm going to keep this line going. So again, what I did was substitute so that I would have to have 18 shirts. Oh boy. What just happened? Oh boy. Okay, I think I'm good. Cool. Okay, I need to stretch this line out again. I'm keeping this recording going, why not? Okay, so I'm going to make 18 across the x-axis. Again, that represented the number of shirts, so 14, 15, 16, 17, 18 is going to be all the way over here, so my graph's probably going to be kind of crummy. That's okay. And I'm going to plot 18, so 18 shirts and 0 pants. I'm going to do the same thing on the other side. So let's assume that I had 0 shirts, which means substitute 0 in for s, so this would cancel out. If I do 25p equals 180, you would need to divide both sides in this case by 25, and you would get a p-value of 7.2. So I'm going to go on this axis to where 7.2 is. 1, 2, 3, 4, 5, 6, 7.2 would be somewhere about right here. Again, I have 2 points, so I'm going to graph these using intercepts, connect all the way over. So at the very end of the problem, we were looking for an intersection. We were looking for 8, 4. So even with my really crummy drawing, I do see that I have a crisscross here. 1, 2, 3, 4, 5, 6, 7. Oh boy, I was a little bit off. This one should be closer to 8 shirts. And then if I look at my value of pants on the y-axis, the number of pants, 1, 2, 3, 4. That one looks a lot better. My x-axis was just a little bit screwy. But again, you do have a clear intersection point because it is a consistent system and it has one solution. Okay, so that was graphing equations using intercepts that were written in standard form. Now this next problem will be a lot easier, a lot less work. It's going to be 2 equations written in slope-intercept form. So let's read through this one. It says a local bowling alley charges $2.50 per game plus $2 for a shoe rental. Another alley charges $2 per game and $4 for a shoe rental. For how many games will the cost to bowl be the same at both places? So here's our cost. We also have the games, and we want to determine what that cost is. So the amount that they charge per game those amounts are different, and so is the shoe rental for both. Now the shoe rental is not going to change. That is a constant amount. So my two variables, one of them is going to be cost. C is going to be our total cost. Let's write total cost here. And I'm going to use G to represent the number of games. Not the price per game, but the number of games. And I'm going to write two equations. So if he goes to one bowling alley, whoever this person is, the cost at one of those alleys is going to be $2.50 per game, plus $2 for the shoe rental. And the other place was charging $2 per game, plus $4 for a shoe rental. So I have two equations in slope-intercept form. Notice that my variable is isolated. It's the same on both sides, and that tells me that I'm going to use substitution. So what I'm doing right here is I'm boxing up what C is equal to, and I'm going to substitute it into this equation on the left. So 2G plus 4 equals 2.5G plus 2. And I'm going to solve this equation by subtract 2G on both sides. So on the left side, I have 4 equals, and on the right side, 0.5G plus 2. In order to solve this now, I'm going to subtract 2 on both sides and end up the left side has 2 and the right side has 0.5 times G. So we're going to divide both sides by 0.5, and G is going to end up being 4. So what that means is after 4 games, the places will be charging the same amount. We want to figure out what that amount is. So it doesn't matter which equation you substitute it back in for. I'm going to use the bottom one. So assume that this person bowls 4 games there. That would be 2 times 4, which is 8, and 8 plus 4 means it would cost $12. So again, final answer. You can say after 4 games, both alleys would charge $12. So what we're going to do then is graph. So across the x-axis, I'm going to have my number of games, and across the y-axis, we have our cost measured in dollars. So both these equations are in slope-intercept form, which make them pretty nice and easy to graph. I'm going to graph the top equation first, just counting by ones. My y-intercept is positive 2, and I'm going to move up in the direction of the slope $2.50 every game. So up $2.50 over 1 for a game, and then up another $2.50 for another game. So now that I have a few points, I'm going to connect my dots. Connect the points. So that represents one of the bowling alleys. So I'm going to do the same thing now for the other bowling alley in slope-intercept form, starting with a y-intercept of 4. And this alley charges $2 a game. So up 2 over 1, up 2 over 1. I have a couple points. And again, once you have your 2 points, we're going to connect the dots. And if I had an actual good drawing, I'm sure we'd have a really clear intersection. But let's highlight that intersection just so that we do understand what this answer means. After 4 games that we had, so after 4 games, the alleys charged $12. So 1, 2, 3, 4 is right here on the x-axis. And if I keep going to see what the y-coordinate is, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So even using the graph, even with my graph being a little bit ugly and off, we can still see that I have one intersection of these 2 lines at the point 412. So again, just to really quickly recap this part, what we did in this problem was write a system of equations that were both in slope-intercept form, and I solved them using substitution.